Hey everyone, my name is Mariam, and in this video I'll be walking through my statistics final project. I used stroke prediction data set from Kaggle, which contains like health information on over 5,000 patients, including lifestyle factors and medical history. Um, my goal was to explore what like factors are associated with stroke risk using just the statistical methods we learned in class. First thing I did was I imported the libraries that I'll be using, so Pandas and NumPy for data manipulation, Matplotlib and Seaborn for visualization, and then stats for statistical testing. Um, I also okay, sorry. So first thing I loaded my data set using the raw GitHub so that the notebook can run independently without anyone needing to like upload. This data set has about 5,000 rows and 12 columns. For the cleaning, so I use the data info to kind of get information on my data set, and then yeah, all of that. For first thing I did was drop the ID column because it was just a unique identifier for like for each patient. It really didn't serve any purpose. I also removed the one row that has other in the gender because I just wanted to focus on comparing males and females if there's any differences there. Next up, I checked for the missing values. We had about 201 missing values from the BMI, and then I filled those using the median BMI from the data set. I chose the median BMI over the mean because the BMI data in health data set tends to be right skewed due to outliers on the high end, and the median is more resistance to that. Um, Next up, I checked for duplicates. There were none, which is good. And then for categorical columns such as gender, marital status, work type, I converted all of those object type into string type, and then I stripped away any white spaces just to make sure everything is consistent. Next up, I applied the Next, I use the dot apply function twice to create new columns. The first is the glucose categories, which group patients into three categories based on their average glucose level. So normal is anything below 100, which pre-diabetic is anything between 100 and 125, and then high is anything between 125. Um, these are like the threshold that are used by medicals. And then the second one is the second column that I created was just to divide the patients into young. Young is anyone under 30, middle is anyone between 30 to 60, and then older is anyone over 60 years old. This just made it easier to compare stroke rates across different ages. Finally, I use the .map function to create a stroke label column that converts the binary stroke column, which just has zeros and ones, into more like readable labels. So it would go stroke or no stroke. Next up for our visualization, I ran the histogram and the Q plots on the three numerical columns, age, average glucose, and then BMI, just to check whether any of them were normally distributed. And then based on the histogram and the QQ plots, none of them follow like a normal distribution. Um, None of them follow a normal distribution enough to just for later on when I'm doing my probability questions. So for this, later on I'll use like a sample. My first main visualization is the bar chart, I just wanted to know which age group has the highest number of strokes. I was yeah, and then from this it's also evident the older people are more prone to strokes than people who are like in the young category. This is very like consistent with what we know like medically about strokes. And then for BMI, second, I wanted to know, look at the relationship just between BMI and stroke probability. And then for this, I used the logistic curve, which shows a high upward trend. So as a patient's BMI increases, so does their risk for a stroke also increases. And then for this, I wanted to know what are the risk factors such as age. So when we combine age, glucose level, and hypertension, is there like a relationship between them? And does hypertension further differentiate factors? For this, I use the scatter plot that looks at age. I use the scatter plot, and then I use the hue parameter, parameter to color points by stroke status. And then this and then just the style. So like if they're a X, they're middle age, circle they're older, and then a square they're younger, and then it will have blue if they had a stroke, and then orange if they did not. Um, so this visualization has more than one dimension encoded in it, and it shows and this just shows that stroke cluster towards the older patients and toward patients with higher glucose, which supports the other graph. So the older they are and the higher their glucose level, the more susceptible they are to having a stroke. And then for our proportion based observation based on normal distribution. So in this section, I calculated four sample probabilities directly from the data. And these are just sample estimates. Um, the first one is overall stroke probability. What is the overall probability that a patient in this data set has experienced stroke? And that's about 4.87 of the patients in this data set, which is about 1 in 20 patients. For next, I calculated the N probability. So I calculated the proportion of patients who had both a stroke and they have hypertension, and that came out to be about 1.29, which is small but meaningful share of patients experience both conditions simultaneously. And then for our OR probability, I calculated the probability of a patient having hypertension or heart disease. And then I used the formal addition rule. So PA plus PB minus PA. And that came out to be about 9.24. It should be. Um, Then I calculated two conditional probabilities. The first was given that patient has hypertension. What is the probability that they had a stroke? And the answer was about 13.25 or 4.87. And then the condition probability was given that a patient is in the older age group. What is the probability they had a stroke? And that came out to be about also 14 point, approximately 17. I think I did the math here wrong. Um, Next probability based on the norm. So I wanted to know what is the probability of a random sample of 40 patients has a mean age greater than 40? And since none of the columns were normally distributed, I had to use a sampling distribution for all three questions of this section. And then So for this, about the probability of a random sample of patients having a mean age greater than 50 is about 2.92, which is low. Because it makes sense though, because the data set is around the mean age for this data set is around 43. So the mean of 50 would be well above what we'd expect. Next, I wanted to know what is the probability of a sample of patients. And so I wanted to know what is the probability of a sample of patients has a mean age between 48 and 55. I calculated that as the difference between these two values, the result was about 9.06. And then lastly, I wanted to know what is the probability that 50 randomly selected patients have a mean average glucose below 110? And that came up to about 72.66, meaning it's likely for a sample of that size to have a mean below 110. Next, for our confidence intervals, I calculated so the first one I use a t distribution because the population the standard deviation is unknown, so we use a sample standard deviation, and I wanted to calculate the confidence intervals for the mean age of stroke victims, and then the result was about 67, like 66.14 to 69.32 years. So we are 95% confident that the true mean age of stroke patients falls somewhere between 66 and 69. So for our second confidence intervals is for the mean BMI for patients who have heart disease. We use a T distribution because the sample is also the normal distribution is also unknown. The population is unknown. And then the interval came out to be about 29.46 to 30.65. So we're about 95% confident that a true mean BMI for heart disease patient falls in that range. And then for our third confidence interval is for the proportion of stroke cases in the overall data set. So for proportion, I switched to a Z distribution, the normal approximation. So because the sample size is large enough for that to be appropriate, both NP and N times one minus NP were well above 5, so the condition was satisfied. And we had about a 95% confidence interval for the stroke proportion, case ranging between 4.28% and 5.46%. So we're 95% confident the true proportion of stroke cases falls in that range. Next up, I ran a hypothesis testing. The first hypothesis testing, I wanted to test whether the mean age of stroke patients is significantly greater than 60 years old. My null hypothesis was that the mean equals 60, and my alternative was that it's greater than 60. I chose 60 because it's commonly that's commonly like the threshold for like elevated risk factors. And the results is that the sample mean at age for stroke patients was about 67.73. So the p-value was well below the 0.5. So we rejected the null hypothesis. And then next we use it for our two sample t-test. We're comparing mean glucose levels between stroke patients and non-stroke patients. So my null hypothesis was that the two means were equal, and my null hypothesis was that the two means were equal, and the alternative was that the stroke patients have a higher glucose level. I used the Welch I use the word t-test, meaning I did not assume like equivariance, which is just safer because we don't know whether the variance are equal across groups. And then the mean glucose for stroke patients was about 132.54, compared to 104.79 for non-strokes patients. So the p-value was also below 0.05, so we rejected the null hypothesis. So stroke patients have significantly higher average glucose levels. For our proportion z-test, so for this, I tested whether the stroke rate among hypertensive patients is significantly higher than among non-hypertensive patients, and the stroke rate for hypertensive patients was about 13.25, compared to the 3.97 of those without hypertension, and the p-value here was also below 0.05, so we rejected the null hypothesis. Next up for our chi-square test, I performed two chi-square tests. The first is a test of independence between smoking status and stroke outcome. Um, um, I wanted to know, is stroke status associated with smoking status? And then for the null hypothesis, was the two variables were independent, meaning smoking status has no relationship on whether a patient had a stroke or not. And then the alternative was that there is a significant association. I use a contingency table showing that the observed counts for each combination of smoking status and stroke outcome. Then I ran the chi-squared and then the p-value. Um, so if P is less than 0.5, then there is a significant association between smoking, and then anything else is there's no significance. Um, and then as you can see, there is a significant association between. So the p-value is less than 5, thus we rejected the hypothesis. So smoking status and strokes are not independent variables. Next up is the our goodness of fit test. So I wanted to know, does the distribution of glucose categories in stroke patients follow an expected distribution? Um, so if glucose category didn't matter, we'd expect stroke patients to be distributed across normally. So between pre-diabetic range and high, roughly like the same between everyone if the glucose didn't matter. My null hypothesis was that the distribution match. Um, my null hypothesis was that the distribution matches the overall data set, and then wait, what was that one? Oh, and then my alternative was that they differ from each other. And then the p-value was below 0.5, so we rejected the null hypothesis. So stroke victims are not distributed across glucose categories the same as the general data set. So high glucose category is overrepresented among stroke victims. And this just kind of reinforce what the data already told us from above, that patients who had a high stroke has a high glucose, they are also more prone to stroke. And then to summarize, this analysis found consistent pattern across every method that we use. So older people who have hypertension and high glucose levels were all associated with elevated risk factors for stroke. And then the confidence interval gave us an estimated range for like um key par key parameters. So the hypothesis testing confirmed the differences between the groups, and then the chi-square testing just showed meaningful association between stroke status in both smoking behavior and glucose. Yeah, that's all. So